So let's pick it up where we left it last time. We had worked through sulfur trioxide and we had worked through the NASA table. Let's walk back through that one more time real quickly. We had done the NASA table for sulfur trioxide. So you would do this just like you did in the lab. And kind of to reiterate here, this NASA is my little invention and it means need, available, shared, and alone. And need is the octet rule for everything except the one smaller than carbon. Available tells you what group it's in. That tells you how many electrons are in the valence shell. And the shared is just the need minus the available. And the alone is just the available minus the shared. And it's these that you use to flesh out the table. And so what we had done for SO3, just to kind of remind people, because we're going to pick it up right there where we left it off last time. My one sulfur needs 8, and each of my 3 oxygens needs 8, for a total of 32 needed electrons for everything to be happy. Available. My one nitrogen brings 6 valence electrons to the party. It's in group 5. It's nitrogen. Ends in 15. It's in the old group 5. It's in group 15, so I'm going to call it group 5. Yes. So it's there. And so, why do I... Oh, that's why it's sulfur. Okay, let's go back. So sulfur, there's a 6 there because we were not dealing with nitrogen. We were dealing with sulfur, which is in group 6. Okay, for a total of 24. So how many electrons have to be shared if 24 things can be shared among 32 people? Well, you've got to share 8 of them. 32 minus 24 is 8. Our rule is we go from electrons to electron pairs and then from electron pairs to bonds. That's our process here. So the first thing we're going to do is 8 shared electrons will make 4 bonding pairs. Just that divided by 2. And then 24 minus 8 is 16. So I have 16 alone electrons, or I can pair them up and make what's called 8 lone pairs. And these are what we use to flesh out our skeleton. Our skeleton was an S with 3 oxygens connected to it. Why did I pick the S for the center? Because if I look at here, S is the least electronegative. It's the thing that's furthest away from fluorine. Okay, that's what you do. Least electronegative is the things that are furthest away from fluorine. And so sulfur is further away from fluorine than oxygen. Oxygen is 1 step from it, and sulfur is 2, so that's the furthest away. So I'm going to use that as what's called the central atom. I'm going to hang these 3 things off of it. 4 bonding pairs. 1, 2, 3. I originally connected them with 1 bonding pair. I have a 4th one. I have to put this 4th one either between this sulfur and oxygen, this one or this one. I chose the one on the right just because I had to pick one. Last thing you do is place your lone pairs. Yes, so you place your lone pairs by this way. Outside in is the rule. You flesh the outside oxygen up till it's got what? 8 electrons. That's what you said you wanted. 1, 2, 3, 4, 5, 6, 7, 8. This oxygen feels 1, 2, 3, 4, 5, 6, 7, 8. This oxygen feels 1, 2, 3, 4, 5, 6, 7, 8. Notice I count to 8 every time. So how many lone pairs did I place? 1, 2, 3 pairs, 4, 5, 6 pairs, 7, 8 pairs. And that's how many I had to place. So I'm done. This is my Lewis dot structure. Now, just as a quick aside, if I had started out with 9 lone pairs and placed 8, the 9th one would have had to go where? On the central atom. And I'm going to show you that in a minute. That's a quick review of what we covered in last lecture, learning to put together a NASA table. And now I want to go over what was covered in the lab, going from a Lewis dot structure to the molecular geometry. So once we had our structure, then the next thing we needed to know was, what is the electronic geometry? So what do? We count the area of high electron density. What is an area of high electron density? It's the number of single bonds plus the number of double bonds plus the number of triple bonds plus the number of lone pairs about the central atom. If you count electrons about the central atom, it will be wrong. If you count the number of pairs about the central atom, it will be wrong. If you just count the number of bonds, it will be wrong because you're excluding lone pairs. You must count this: the number of single bonds, the number of double bonds, the number of triple bonds, and the number of lone pairs. Each of these counts as one area of high electron density. So with that, let's go back and review what we had. So we can see about the central atom, we have one single bond, two single bonds. Let's keep count, two single bonds. How many double bonds? One double bond. Remember, I'm not counting pairs, I'm counting bonds. One double bond, and I don't see any lone pairs, no triple bonds, and no lone pairs. So what do I have? A total of 3 areas of high electron density. The furthest thing 3 things can get away from each other is trigonal planar. Okay? Or if nothing else, you memorize it. 3 areas of high electron density is trigonal planar. So that is the electronic geometry, trigonal planar. Now, how many lone pairs do I have? Well, of those 3, none of them were lone pairs. So what that means is I can put an oxygen on the end of each of these pegs because none of them are lone pairs. And since I didn't change anything, I didn't hide anything. See, if one of these had been a lone pair, I would have had to hide it, and it would have given me a different shape that's left. But since none of them are lone pairs, I didn't hide anything, so I still have trigonal planar. So that's also the electronic geometry. Now for the new part and the last part. How do you calculate the polarity of the molecule? How do you know if it's, quote, lopsided or not? Well, there's 2 things that can make it lopsided. And let's envision that. So let's say we have a central atom here, and we have something, and let's pretend it's a rope pull, right? There's a rope with a knot in the middle of it, and you have 2 people pulling each way. And if they pull with exactly the equal force, then if they pull with exactly the same equal force, then this knot's not going to move. What that means is if they pull with exactly the equal force, then it's equal all over and it's nonpolar. So this is my little device that I kind of help myself just envision in a quick glance whether something is going to be polar or not. If I can put things on the end of that and the knot in the middle doesn't move, then it's nonpolar. If I do something and that knot moves, if one side pulls harder than the other, then it's lopsided, and that means it is polar. So let's look at the scenarios. So this is a linear, we'll take a linear molecule. I'll do it in a minute for trigonal pyramid and tetrahedral. But let's take this. And let's say we have person A here, and we have person A here, and they're of equal strength. Well, this is going to be nonpolar. Why? Because if 2 people pull opposite each other, exactly opposite with the same force, they're going to cancel each other out. Okay, let's take another scenario. So a lot of this is common sense, and I'm going to distill this down to 2 simple rules. Okay, so let's say we have 2 people, A, pulling on a rope, and one of them walks around and pulls from a 90-degree angle. Well, guess what? Well, if 2 people yank that rope and they're standing in the end of it's to the side of both of them, of course, what's going to happen when they pull it? It's going to stretch out between them, right? That knot is going to move in between them as the rope stretches out. Yes? Okay. So in this case, this molecule, if it were shaped like a 90 degrees, it would be polar. So let me give you one more scenario, and then I'll give you the 2 rules. Okay, so the next one is, let's say we have our same rope, and it's linear. They're opposite. And this time, person A pulls on this end, and person B, who is much stronger, pulls from this side. Well, what's going to happen to the knot? Well, you know it's going to happen. It's going to what? It's going to move toward the stronger person. Yes? Okay. So we see two scenarios that will move the knot. We see two scenarios that will make it polar. One is the direction of pull. Are they pulling opposite each other, or are they not pulling opposite? So that's called symmetry. Okay, that's called symmetry. If they're pulling exactly opposite each other, we say that's symmetric. In other words, if it's symmetric, they're going to cancel out. Okay, so that's the first thing. So we have to worry about symmetry. The next thing we have to worry about is, even if we have the right symmetry, and you see these top two examples, they're pulling exactly opposite each other. So the symmetries are going to cancel each other. That's symmetric. Okay? But guess what's not the same? On this top one, it has the symmetry, but the end group, the person pulling it, the end group, the thing that's attached to the central atom, if the end groups pull at with a different strength, then it's going to be lopsided. So I have the thing here called EG for end group. Okay? It really should be like electronegativity. And that's how an atom. Now I'm using the example of a person pulling. Okay? Different people with different strengths. Well, how do you measure the strength of an atom pulling on electrons? That's what electronegativity was all about. And now you know. That's just how strong it is. Nothing stronger than fluorine. Fluorine always pulls harder than anything else. The second strongest element in the whole periodic chart is oxygen. Yes? So this is the strongest. This is the next strongest. And then they get tied for third with these two, and then tied for fourth, I guess, something like here. And then this is fifth. And you know electronegativity increases from bottom to top. Okay, and it increases from left to right, and that's order of increasing, stronger. Okay, and we kind of neglect the noble gases because they're not sharing electrons at all. They're fat and happy by themselves. So fluorine is kind of my reference point. That is this big man on campus. That's the strongest one. Okay, that tells you which end of the molecule is going to be negative. So you already intuitively know that, or at least intuitive. From what we talked about earlier, you know that. But now we're kind of looking at the direction. How does that affect the molecule of the whole, each bond? So see, this is a bond, and that's a bond. Those are both bonds. So what the polarity is looking at is all of the bonds of the overall molecule. And we look at the central atom. Okay, so here's when something's going to be polar. Let me give you a test for nonpolar. So look at this. What makes this nonpolar? Two things make it nonpolar. It has symmetry. I'm going to check the box down. It has symmetry. Yes. In other words, they're pulling opposite each other, and they have the same end group. In other words, they have the same electronegativity. In other words, they're pulling with the same amount of force. So anytime somebody pulls opposite each other, exactly opposite, and they pull with the same force, nothing's going to happen. It's nonpolar. Okay, let's look at the top situation. What happened there? It passed the symmetry test. Yes, they're pulling opposite each other. But it did what? It failed the end group test. One's pulling harder than the other. And so therefore it's a polar compound. This is polar. Okay, why? Not because of the symmetry, but because of the end group. Now let's look at this bottom one here. This one at right angles. So it passes the end group test. The A's are pulling equally hard, but look what it does. It fails the symmetry test. These are not pulling opposite each other. If it fails either one of those, then it's polar. So you can look at this either way. Both of these have to be true. The symmetry has to be true, and the end group has to be the same for it to be nonpolar. If it fails either one of those, then it's polar. And that's really all there is to this polarity thing. Okay, so let's see. The only thing I think I need to add to that is, how do you know if something's symmetric? And here we go. You know there's only 6 choices you have in this class. You have 3 choices of electronic geometries, and you have a total of 6 choices of molecular geometries. Symmetrical, see that symmetrical? What that's there for is to tell you of the symmetrical configurations, anything that's an electronic geometry is symmetrical. In other words, if it's linear, if it's trigonal planar, or if it's tetrahedral, it passes the symmetry test. Okay, and I'll try to prove that to you right quick. So, if A pulls here and person A pulls here, they're pulling opposite each other and they're pulling with the same force. The knot won't move, and so therefore linear is symmetric. Okay, let's do the next one. Here we go. A pulls here, A pulls here, and A pulls here. If you have a rope, if you have 3 ropes and they're tied in the center, and you have each person stand 120 degrees apart and they pull with the same force, the knot won't move. In other words, trigonal planar is symmetric. Tetrahedral, same thing is true. If you have people stand with 4 ropes and they're a tetrahedral apart from each other and they pull with the same force, it will be symmetrical. So remember those. Those are your 4. Now, how about bent 120? Well, no, that's asymmetrical. It's not symmetrical. How so? Well, if you have 2 ropes and you have people stand 120 degrees apart and they yank, that center is going to go flying that way. Yes? Okay. So that means that bent 120 is not symmetrical. The same thing for bent 109, and the same thing for trigonal pyramid. If 3 people are on each end of this pyramid, this rope, and the knot's kind of up in the air a little bit, and everybody yanks on it, that knot is just going to go flying back down to level with them. So that's not symmetrical. Okay, so that's how you can look and see if something is symmetrical or not. Okay, there we go. So let's now do a similar one, but that's different. All right. So I want you to see the contrast. Instead of SO3, we're going to do SO3 minus 2. SO3 was sulfur trioxide. This is not. This is what? Sulfite ion. Remember, that's sulfite, because it comes from sulfuric acid. Kind of reviewing for the final here. I'm sorry, it comes from sulfurous acid. Ite ions come from us acids. And we know that's sulfurous because one of our memory acids was sulfuric, which was H2SO4. All right, that's a little trip down memory lane that you'll want to know. And this was sulfuric acid. So on a test, an easy question supposedly would be name this ion. That's the chapter, whatever it was, 4 or whatever. Or the question could be, draw me the Lewis dot structure, or worse still, tell me if sulfite ion is polar or not. Now here's why polarity is a pretty hard question. Because if you're asked a polarity question, you got no choice but to do every one of these steps. Every one of them. Okay? So when you're practicing these, you may want to always see if the question asks what the electronic geometry is. You might want to see if you can go ahead down to polarity. So polarity is an A-level question because you got to do everything. You can't make a mistake anywhere. So this is kind of an A-level question. And these are kind of B-level questions. And these, to be honest, are just kind of C-level questions. Okay, so that's how the difficulty breaks down. And I want you to see why polarity is harder. It's not harder in terms of the concepts. It's just harder in that you have more steps that you have to go through to get right. Okay, so let's go back to our SO3. Now, because I have tremendous problems trying to write with a mouse on this, I had worked this out before. And so even though it's messy, I'm going to kind of talk you through this as best I can. And maybe I'll erase a few things as I go. Okay. So, yeah. So we'll work through this. Okay. So let's do this. SO3 2 minus. So let's start out and do our NASA table, right? Follow it. First thing's a NASA table. What's my need? I have 1 sulfur and it needs 8. And I have 3 oxygens and each one of those need 8. So I need 32 electrons, just like before. No kidding, because I've got the same number of atoms. But here's where it starts getting different. And this is going to change everything all the way down to the polarity. Okay, what do I have? I have 1 sulfur and it brings 6 electrons to the bring your own electron party. And each of my 3 oxygens brings 6. So that's a total of 24. So it's a total of 24. So let me do this. So these bring 24. And that's where we stopped last time, was 24. But guess what else you have? A -2 charge. What does that mean? I've got to add those in. It means I have all of these, plus I have an extra 2. So I have to do what? I have to come back and I have to add my extra 2 right there. So that's one of the things, one of the tripwires you had to look for when you're doing your NASA table. What 2 things do you look for? The smaller than carbon exceptions, the ones that don't obey the octet rule, and the ones that are ions. Anytime you have an ion, you're going to have another digit here. And just to remind you, had this been a +2, you would have subtracted 2 here. Why? +2 means you lost 2 electrons. And so you would have subtracted these because the NASA table counts electrons. Okay, so there we go. So we have what same thing we had before with SO3, but we added 2. Now we get 26. So what does this mean? 32 minus 26 is 6, which means we only have 3 bonding pairs. Okay, I'll put that in my mind as I draw my Lewis dot structure here in just a second, okay? And then how many alone electrons do I have? 26 minus 6 is 20. So I can make 10 lone pairs. That's supposed to be 10, and that's supposed to be 10 lone pairs. Okay, so this is what I need, right? These are the numbers that I need to flesh out my Lewis dot structure. So what do I need? 2 things. I need the bonding pairs from the table. And again, I'm not going to use any of this information anymore. I'm done with that. We're done. Okay. And I need what? A skeleton. So what's my skeleton? I've got an S and 4 oxygens. So you can think about it as being this way. Just any nilly-willy order. Okay. And now I need to connect all these together and pick one of them to be the central atom. Well, what's less electronegative, oxygen or sulfur? Sulfur's less electronegative, so I'm just going to put sulfur in the middle. And it doesn't matter what shape I make. I'll get the right shape later. I have 3 oxygens connected. Okay. Now it's just a matter, I have a skeleton. I have my bonds. Now it's just a matter of fleshing it out. So let's see what we have. I have 3 bonding pairs to place. And how many bonding pairs do I have placed? 1, 2, 3. Oh my gosh, I'm done. They're already placed. I've got 10 lone pairs. Okay, well, let me just start. Outside in. So let me start placing some electrons here. And let's see. Maybe we'll stick with green electrons. Okay. Okay, so here we go. Ready? So let's start from the outside in. And how many does oxygen need? You said up here it needs 8. So this oxygen fills how many? 1, 2, 3, 4, 5, 6, 7, 8. Okay. Moving around. This oxygen needs to fill 8 because it's one of the 3. It fills 1, 2, 3, 4, 5, 6, 7, 8. It now obeys the octet rule. And let's go to this one. This one needs to fill 8 electrons, and it has 1, 2, 3, 4, 5, 6, 7, 8. Okay, let's see how we're looking. That looks pretty much like it did before, so let's go counting this now. I used, how many lone pairs did I just do? That's 1, 2, 3 pairs, 4, 5, 6 pairs, 7, 8, 9 pairs. Okay, I used 9. Uh-oh, I got 10. I used 9, so what do I have left over? 1 lone pair left over. And where does it go? I got no place to put it. I have to put it on the central atom. Why? Because this has already got 8, that's already got 8, that oxygen already has 8, and if it's got 8, it wants no more than 8 and no less. Outside in. Okay, so now, is this my Lewis dot structure? Almost. You're almost there, but you need to do what? Now you know you have 2 charges, a negative 2, 2 electrons extra floating around in here. Which 2 of these are extra? I don't know. Well, how are you going to declare it? You put brackets around the whole thing, and you put your charge up here. -2. And what this says is I've got, this is my Lewis dot structure. And just so you know, somewhere in those brackets is an extra 2 negative charges in there. Somewhere in there. I don't know where they are. But they're in there. And so that's what the bracket and the symbol mean. Anytime you have an ion, you need a bracket and symbol. Okay, so there's that. Now let's just continue on. And let's go to the next step and say, okay, so what did we do on our cascade after that? We determine electronic geometry. So what do we need to know? The first thing we need to know is, and if you've forgotten, let's go back and see if we can. Okay, that might get in the way in a little bit, but I'm going to leave it there at any rate. Okay, so what have we done so far? Kind of end review. Oh, zoom up. Yes, okay. So what have we done so far? We started out with a formula. And we did a NASA table. And we paid it, and we also did find one of our exceptions was useful. This was an ion, so we caught that. And we also made a skeleton. Yes, we made a good skeleton. We made sure our electronegativity was there. We placed all of our bonding and lone pairs. We were very, very careful to count and make sure we saw we had an extra lone pair, so we dumped it on the central atom. Then we drew our Lewis dot structure. That's where we are. And what's the next thing we're going to do? We're going to count areas of high electron density so we can determine the electronic geometry. All right, so here we go. We are going to count do the 4 count thing. We're going to count the areas of high electron density about the central atom. That's a tripwire, about the central atom. When you go down here, that's a tripwire. About the central atom. Okay, there we go. You have been warned yet again. Okay, so let's look at the central atom. Let's see what we got here. There's the central atom. Right? Every electron, every bonding pair that touches it, it gets to count toward it. Okay, so let's do our 4 count thing and see what we got here. How many single bonds do you see? I see 1, 2, 3. How many double bonds do you see about the central atom? I see none. How many triple bonds do you see? I see none. How many lone pairs do you see? I see 1. For a total of 4 areas of high electron density. And if you have 4 areas of high electron density, what is your shape? tetrahedral. Okay. I should have typed that. Okay. It's tetrahedral. It's this shape, basically. I'll just put it there. Yes. Now, on the test, you're going to do a answer choice, and it's going to say tetrahedral. It's not going to ask you to draw anything. But this is what it looks like, right? Okay. So you now have the electronic geometry. Let's go to the molecular geometry. So now what do we need to do? Let me zoom up again over here. And so we can see it. Okay, so let's go over here. And what do we need to do now? We have the electronic geometry. That's tetrahedral. We need to now see how many of those four areas of high electron density were lone pairs. And then I'm going to ignore them and see what shape is left. So the easiest way to do that, I think, is this. I'm going to take this tetrahedral. Now I'm doing molecular geometry, so I'm going to draw you a graphic of what I think in my mind's eye. Yes, so now this is just the electron structure. I'm now going to fill it out with atoms and molecules. I know I have a sulfur at the center. I'm going to put the sulfur there. See, the electronic geometry only sees electrons. The molecular geometry only sees atoms. So let's flesh this out. There's the sulfur. I have one of these is got to be an oxygen. Doesn't matter where I put it. That's that oxygen. See, I know the sulfur also, one of these areas of high electron density has an oxygen attached to it. And I know a third one, area of high electron density, has an oxygen attached to it. And the fourth area of high electron density is what? A lone pair. But what does the molecular geometry not see? It doesn't see lone pairs. So I'm just going to hide this. I'm not erasing it, I'm just hiding it. And some of you memorize, but I don't. Now what's left? You can see what the shape is now. It's no longer tetrahedral, it's what? Trigonal pyramid. And that's all there is to work in these things. That's trigonal pyramid. So the molecular geometry, you flesh it out. You flesh your electron skeleton out. And everything that has an atom on it, you can still see. And everything that has a lone pair, it's still there. It's still pushing all these oxygens down. But you can't see it in the molecular geometry. You can only see what's there. And so the shape you now see, if you ignore the black, again, not erasing the black, you're not losing the electrons. They just become invisible. So what you see now is what? Trigonal. Okay, there we go. So that's your shape. Now, let's finish it up. So what's the last cascade? Okay, let's come back over here and let's look at our very last one. We're going to go from molecular geometry now to what we just learned was polarity. And what's our trick there? We're going to see if we have the same N group and if we have the symmetry. And that's what we're going to do. We're going to do a check. And if it fails either one of those, if it fails the symmetry test or it fails the N group test, then it's what? Then it is polar. If it fails either one of those, so let's go back and check. Okay, so I'll do polarity this way. Okay, polar. So the question here is, see, what was this? I was coming down here looking for electronic geometry just to kind of clean this up a very little bit. And here I was looking for the molecular geometry. Okay. And here I'm looking for the polarity. Okay, just so you can follow this later. Right. So what's the polarity? So let's look and see. Let's do an N group test. Yes. And see if it's pass or fail. And then we'll do a symmetry test. See if it passes or fails. Okay, here we go. Does it pass the N group test? Yes, it does. Why? Because every N group, every pendant group, every group that's hanging off the central atom is exactly the same. They're pulling with the same force. It passes the N-group test. It passes the electronegativity test. They all have the same electronegativity. Does it pass the symmetry test? Well, you can look at that and see it's lopsided. No, it fails the symmetry test. Why? Same reason before, because if these are ropes and all three of these guys pull, guess what's going to happen to the knot? Boom, it's going to move. Okay? Not to mention, it just looks lopsided. Yeah, okay, there's that too. It just kind of looks like a whole lot more of the atoms are on this side of the equation than that side of the of the molecule than that side, and that's true. So sometimes you can tell by looking, but sometimes not. Okay, so there we go. So you would say this is polar. So now let's review this. So what do we have here? What we have is a trigonal pyramid molecule that is polar. That's what you came up with. Okay, that's a slow roll through a long one. Now notice, this was polar and it was on a tetrahedral framework, but what was SO3? SO3, not SO3 2-, but SO3 was a totally different deal. It was what? A trigonal planar molecule, and it was nonpolar. So you put those extra 2 electrons, it totally changes the chemistry. It's a totally new animal. The difference between SO3 and SO3 2- couldn't hardly be larger. So that's why you have to pay attention to those details. That's why it's really, really critical when it says, do you see an ion? Let me go back to our little table there that I had. Oh, there it is. Okay, that's why you want to pay very attention, and that's why I took a lot of care to write this out, is every exception. See, if you did the SO3 and you missed the ion exception, all of this would have given you the results for SO3, not SO3 2-. It would have given you for sulfur trioxide, not for sulfite ion. Okay, so that's about as good as I can do for you. Let's see. Okay, let's see where we're at. Right. I did want to give you an aside on one of these and talk just a little bit about water. You now are going to do water in your lab. I think that's one of the questions you had. And what you're going to find out is water is polar and it's V-shaped. All right, so I'm going to draw the V's in there. And those V's are supposed to be about 109.5. So I'm going to draw each water molecule there. And you can see how they're stacked. And you also see water is polar. Well, because what? It's a tetrahedral. So what water is, it's a tetrahedral, just so you know. Water is on a tetrahedral framework. Yes? And what you're going to find out is, if you look at it, is 2 of these are H's about the central atom, and 2 of them are lone pairs. So it has 4 areas of high electron density, but 2 of them are lone pairs. And when you hide the lone pairs, guess what shape you're left with? Ignore what's in black. Yes. And then you'll see, and I'll put my oxygen there so you can see it. And you can see oxygen is kind of a boomerang. It's bent 109.5. Okay, and that's what I'm trying to show you here with each of these. So here's what happens. So, and you find out it's polar. So what the polar really is telling you here is that this end of the molecule, oxygen is more electronegative, is kind of sort of negative. And this end of the molecule is kind of sort of positive. So what happens is, so this end is kind of sort of positive. So this positive of one kind of connects to the negative of the next. And then one of these positives connects to the negatives. And so what happens is, water is very, very unique in that it's structured. Those bond angles and the amount of those charges is just enough so that 6 of them can make a ring, and that ring is pretty darn stable. So they make a ring. And this is why water is one of the few elements in the universe that when it freezes, it floats instead of sinks, which is a good thing. Because if water behaved like most other things, when it froze, it would sink. Ponds and oceans would freeze from the bottom up and kill everything in it. So this is really an important point, that water behaves this way. So why does it float? Well, because it's less dense. Why is it less dense? Because when these charges and these bond angles are just exactly this whole structure actually takes up more space than just 6 water molecules that are floating around nilly-willy in the water. And because it takes up more space, but it's the same mass, it has a less density. That's why water floats. But that's not, so very few people know or understand that. It's just a real odd thing. Matter of fact, I think a lot of people think usually when you make a solid, it floats. No, normally when you make a solid of something, it sinks in its liquid. Water is a very rare exception. But I want to show you something else that's kind of cool. This really is. Okay, here we go. So how many sides does this thing have? 1, 2, 3, 4, 5, 6, right? See, that's 6 sides? If a water molecule, when it freezes, does this, it's going to make this shape. Looks kind of like what, a hexagon? Yep. And so there's 6 faces on that. How many arms does a snowflake have? Every one of them. They're all shaped unique, but guess what they all have? 6 arms. And now you know why. Every snowflake starts from one of these arrangements, and they just build out from there. And that's why every snowflake is 6-sided, because they start from this. So, kind of cool. So you can see how the geometry of just 6 individual molecules can influence the shape of something that's so big that you can see it with the human eye. Okay, and so that's not the only reason, of course, but that is a very good illustration of why this stuff matters. How charged it is, how lopsided it is, how polar it is will determine how much one molecule adheres or sticks to another. And so the more it sticks, the more viscous it's going to be. So you could do this same type of rationalization, and you could kind of rationalize why it is syrup moves really slow and it's really, really viscous, and other things aren't. You can track that back to a large extent to the shapes of the molecules and to how polar they are, because that will affect how tightly they're hanging on to each other. And how tightly they're hanging on each other determines whether it flows. Things that hold together real tight don't tend to flow. Yes. What the boiling point is, things that hold on to each other really, really tightly, they typically have a higher boiling point. In other words, you've got to have more heat to make it go into the vapor phase. Okay. And with that, I believe that's everything that we need to cover with respect to Lewis dot structures. That's the end of the material.